So we're going to be looking at inverses of relations here. If a relation consists of an order pair or order pairs x, y, then its inverse is all order pairs y, x. So one way to look at finding the inverse is simply just switch x and y. X and y become inverted, and all the operations that happen to the variables become inverted as well. Well, if we're switching x and y, then what is the domain of the inverse was the range of the original function, and the range of the inverse is the domain of the original function. Since x and domain are connected and y and range are connected, if you switch x and y, domain and range switch as well. And the last little note on the vocabulary here is f-1 is a way of denoting that a function has an inverse, and we express it as f-1. This is similar to like the trig functions that you might see on a calculator where it says sine of x. You may see right above it sine -1 of x. Those two are inverses and will cancel each other out. Some other inverses that you might know or be aware of are additions, inverse is subtraction, and multiplications, inverse is division. Okay, in this example, we're going to find the inverse of each relation and then determine if it's a function or not. Well, the easiest way to find the inverse is just to switch the x and y values. For an order pair, that's pretty simple. Just literally switch the x and y value. So the first order pair will become 2, 1. The second order pair will become 4, 2. The third order pair will become 6, 3. And the fourth order pair will become 8, 4. If we look at this, we're also asked to determine if the inverse is a function, and in order for it to be a function, the x can't have more than one y value. So if we look at all the x values, none of our x values are repeating, so the inverse is a function. Now part B, doing the same kind of thing. If we find the inverse by switching x and y, we get 5, 1, we get 6, 1, we get 6, 3, and we get 9, 4. So this is the inverse relation, and to determine if it's a function, we just have to look to see if any of our x values here are repeated with a different y value, and we can see that we have 6 in 2 of the order pairs for the x value, so the inverse is not a function this time. So in this example, we're going to find the inverse of the function f of x equals 3x minus 2. Well, the first step for us finding the inverse will be to switch x and y. Now you can see that there is no visible y. However, remember that f of x and y are pretty much interchangeable. So while it says f of x equals, that's another way of saying y equals. So if we switch x and y, we're going to turn it into x equals 3 times y minus 2. Now we just have to get y back by itself so that we know the inverse equation. So we'll get rid of addition and subtraction here first. So we have x plus 2 equals 3y. And then to finish getting y back by itself, we'll divide both sides by 3. In doing so, there's a couple ways to express the final answer. We'll have y by itself equal to x plus 2 over 3. An alternative way of doing it is dividing each term individually by the 3. So we could also write it as y equals x over 3 plus 2 over 3. And there are additional ways of writing it as well. So one of the ways to represent the inverse is the f-1. So instead of having the y here, we could also write it as f-1 of x equals x plus 2 over 3. And of course, we could also write it as f-1 of x, saying the inverse of f is x over 3 plus 2 over 3. So any of these four versions is acceptable as far as the final answer goes. In this example, we're supposed to find f-1 of x if f of x equals the square root of the sum of twice x plus 5. So in order to do this, remember that f-1 is just saying inverse. That's a mathematical notation. So we're going to find the inverse here, which means to start by finding the inverse, we're going to switch x and y. Remember that f of x is another way of saying y, so we have y equals. So we're going to switch x and y, making it x equals the square root of 2y plus 5. From here, we're going to have to solve this equation. So there's nothing outside the square root. So to get rid of the square root, I will square both sides. X squared is simply just x squared equals squaring and square rooting will cancel. We'll have 2y plus 5. Now we should just have a two-step equation. So we'll subtract 5 from both sides. X squared minus 5 is just simply x squared minus 5 equals 2y. And then we'll divide both sides by 2 here. And again, a couple ways to write it. So we have y equals x squared minus 5 all over 2. We could break it up into two fractions as well. Since it does use the f-1 notation, I would probably prefer it as an answer like this. X squared minus 5 over 2. And again, you can break it up into more than one fraction. Now there's also something else we have to consider. This is a square root function. So square root functions, we have to consider its domain and range as well. So a square root function doesn't exist everywhere. So we have to impose restrictions on the domain of this quadratic, because for a square root function only contains like this part of the parabola. However, a quadratic function contains the full parabola. That's not very well drawn. So we have to restrict our graph so that we don't have this portion of the function taken into the quadratic. So since x and y are changed, we need to look at the range of the original so that we can impose restrictions on the domain of the inverse. So if we're talking range of the original, so the original function is a square root function. Square root function's parent function has a range of y greater than or equal to 0. There is nothing outside, so there's no transformations on this, which means the original range is y greater than or equal to 0. Well, which means when we switch x and y, the original range becomes the inverse function's domain of x greater than or equal to 0. So we need to impose this restriction on the domain because the shape of the quadratic graph is not the same as the shape of a square root function's graph. Okay, in this example, we're going to find the inverse of y equals x squared plus 5. And it also has a note on the side. We have a specific domain of x values greater than or equal to 0. We're going to address what it would look like both with and without this here. So as I go through doing this, the first step in finding the inverse is to switch x and y. So my y equals is going to become x equals. My x squared is going to become y squared plus 5. Now we just have to go through and solve. So I will subtract 5 from both sides. X minus 5 is simply just x minus 5 equals y squared. Now, to get rid of the squaring, we'll look at square rooting both sides. However, when we do this, we have to consider both the positive and negative variations on the square root. So we'll have plus or minus the square root of x minus 5 equals y. Now, this is going to take a second to talk about. If we were to look at this graph on Desmos or another graphing application, we can't actually graph it with the plus minus. In reality, that plus minus is doing two things. So if I graph this, the positive version is the upper half, or the 1/2 of the quadratic, while the minus version is the lower half of the quadratic, or the parabola shape. So we have to actually look at this a little bit closer. This is no longer a function because it does not pass the vertical line test. Now, where the little notation about domain here comes into play is it's saying x values are greater than 0. Well, whenever you switch x and y, that becomes y values are greater than 0, greater than or equal to 0, which means the inverse is talking about is only the positive version, because the y values would be greater than or equal to 0 for that case. So the inverse of the function given is y equals the positive square root of x minus 5. And this one is an inverse function as well as just an inverse. However, if this was not included in the original problem, then the inverse would consist of the plus and the minus here. So to summarize, without the stipulation of x greater than or equal to 0, the answer is just y equals plus or minus the square root of x minus 5. But with the addition of that restriction, we are just taking the positive version. Okay, so this is just some vocabulary with one-to-one function. A one-to-one function is a function that has each x value only having a single y value, and each y value is only paired with a single x. So no repeated x values and no repeated y values. One of the ways of determining if a function is a function from a graph is using a vertical line test, where you draw a bunch of lines going down through, and if any of the lines hit it more than once, it is not a function. Well, if we're looking at the inverse now, we can take a look at the original graph and do a horizontal line test. And if it passes both the horizontal line test and the vertical line test, then it's a one-to-one function. If it fails the horizontal line test, then its inverse is not a function, because when we find the inverse, it would be something like this, and you can see that the inverse would not be a function. But if it passes the vertical line test and the horizontal line test, for example, just a straight line would do that. The inverse of, I shouldn't use that one, that's a horrible one to use as an example. Let's see, a better one, square root function would work. So like that. The inverse of it is this. So if you draw vertical lines, you can see that it doesn't touch more than once, and if you draw horizontal lines, it doesn't touch more than once. Therefore, it's a one-to-one function, and both the original and its inverse would be functions. So in this example, we're going to be doing two things. We're going to first determine which graphs have inverses that are functions, and we're also going to sketch the inverses. So first, to determine if the inverse is a function or not, we're just going to use the horizontal line test. If we draw horizontal lines on the graph and it touches more than once, then the inverse is not going to be a function. The first one, if you draw horizontal lines, you can see that it hits twice, so the inverse is not a function. On the right graph, no matter how many horizontal lines you draw, it only touches the graph in one place. Therefore, the inverse is a function. Now, either way, here we're supposed to sketch the inverses. And to do that, well, the way we've been finding inverses the whole time is by switching x and y. So we're going to do the same thing, just take some ordered pairs and switch x and y. Remember that if it's not a straight line, you will have to choose some points that will help you figure out the shape. So like on the left one, it's a quadratic graph. I'm going to choose this point here, which is 0, 0. I'm going to choose -1, 1. I'm going to choose 1, 1. I'm also going to choose another points because the ones kind of get a little confusing. So I'm going to also choose -2, 4. And then +2, 4 to help me get the shape. Well, to find the inverse, we simply just switch x and y like we've been. 0, 0 is going to, well, stay 0, 0. Let's use a different color, make it stand out a little bit. There we go. -1, 1 is going to become 1, -1. if we switch x and y. 1, 1 is going to, well, stay 1, 1. Negative 2, 4 is going to become 4, 2, 4, negative 2. And then lastly, 2, 4 is going to become 4, 2. With this, we have enough information to draw it nicely. And there we go. Now for the other graph over here, if we do the same thing, since it's a straight line, all I really need is 2 points. So I'm just going to pull this point here, which is the point negative 2, negative 3. And I'll also take the point 0, 1. If we switch x and y for these, we're going to have negative 3, negative 2. So negative 3, negative 2 is right there. And 1, 0, which is right here. Connecting those and drawing the graph in best I can. There we go. Now some extra additional properties with this is the inverse and its original graph are actually reflections across a specific line. The line that there are reflections across is the line y equals x. Which is the identity function. Which many parts of math have identities. For example, addition has identity. If you add 0 to anything, it doesn't change the value. Well, the identity function is if you plug in 5, you get out 5. You get the same thing back. Since inverses are opposites and cancel each other out, the composite of the two would return what you originally plug in if they are inverses. Okay, in this example, we're going to verify that f of x, which is equal to 2x minus 5, and g of x, which is the sum of x and 5 divided by 2, are inverses. One of the ways of doing this is using function composition. Because if you do f of g of x, and they cancel each other out, resulting in just receiving x, which is the identity function, and you also do g of f of x, and it also results in x, the identity function, then the two are inverses. Identities or inverses operate together and cancel each other out to create the identity. For example, addition 5 and its additive inverse, which is negative 5, gives you 0, the additive identity. The multiplicative identity would be multiplying by the reciprocal, 1 over 5, or dividing by 5, which would give you 1, which is also the identity. 1 is the multiplicative identity. Well, the identity for functions is x, where you get out what you put in. Now, the reason why we have to do this for both f of g and g of x is the fact that composite functions or composites of functions are not commutative. The order actually does matter. So unlike having negative 5 plus 5 and 5 plus negative 5, those are always going to be the same thing. Well, f of g and g of f are not necessarily going to give you the same thing. So we're going to just have to check both f of g and g of f to see if we get x. And if we get x on both of them, they are inverses. This is a verify question, so it's already telling you that they are inverses. You just have to show it. So verify questions are always telling you that it's true. You just have to prove that it's true with the algebraic work or listing the properties. Okay, so let's get started here. So on the left, we're doing f of g. So f of g of x, the outside function is f. So we're going to do 2 parentheses minus 5, and then g of x is going inside g of x is x plus 5 over 2. We'll simplify this. Well, 2 is connected by multiplication to the parentheses. It's a whole number. The whole number on top is going to cancel out with the division on the bottom, leaving me with x plus 5 minus 5. And then we have to combine like terms. Positive 5 and negative 5 also cancel out, leaving me with x. Now I do have students, or I've had students in the past, try to cancel things out all right here. They would go, oh, 2's cancel, and then the 5's cancel. But that's not verifying it, because it looks like you did it all at the same time. Verifying is showing the steps that allows it to happen, and proving that happens, not just understanding that it does. So you do have to actually write it out in separate steps to verify and show that why it's happening, why it's true. So yeah. Okay, but that is only the first half. We have to do this for both. So I now have to go back and set up g of f. So my outside one is g is x minus 5 over, or x plus 5 over 2. So we're going to do x plus 5 all over 2. And inside the parentheses, we are going to be putting our f equation, which is 2x minus 5. Now with this setup, there's nothing connected to the parentheses by multiplication. This division is connected to not just the parentheses, but the 5 as well. So the parentheses are kind of useless here, so we're going to ignore them and just combine like terms. When negative 5 and positive 5 combine, canceling each other out, leaving with 2x divided by the 2. The 2's can also be canceled out, leaving me with just x in the long run. So both sides have indeed simplified to be x. Therefore, we have successfully verified that these two functions are inverses of each other.